Hi, I'm Jens Henriksen, and this is going to be a little introduction, deep dive into mathematical induction, and specifically some of the things you have to be careful about when using it to prove something. The way that we're going to do that is with a very famous example of faulty induction, which is proving that all horses are the same color. Obviously, this is ridiculous, but that's kind of the point of this, is to demonstrate that ridiculous statements can be given seemingly a true proof. And the way we're going to do that is with the standard formula for induction, which is you find a base case, an induction hypothesis, and then you prove the induction hypothesis. So to start our proof off, we're going to let P of n be the statement, any collection of n horses is the same color. So for our proof, we started off with the base case, P of 1, which in this case is a collection of one horse is one color. That's obvious, that makes sense, that's intuitive. A collection of only a single object has to just be the characteristics of a single object. So for our hypothesis now, our induction hypothesis, we assume that P of k is true, and P of k is the statement, a collection of k horses is one color. Obviously we can't assume, well, it doesn't seem like we can assume that, but because this is induction, we're allowed to do that because we just need to prove that P of k plus 1 is true for the domino chain knocking down after each other. So to prove that P of k plus 1 is true, we're going to consider a set of k plus 1 horses, which is going to be horse 1, horse 2, etc., to horse k, and then horse k plus 1. Now we're going to split that up into two sets and individually consider those. So we're going to split it up into two sets of k horses specifically, which is h of 1, h of 2, etc., h of k, and h of 2, h of 3, etc., h of k plus 1. Now something you might notice about these sets is that they both contain k horses, because this is horse 1 through horse k, and this is horse 2 through k plus 1. And because of what we assumed up here, we can assume that both of these sets are only a single color per. So that's great, but that doesn't help us prove this until you can notice that there's significant overlap from h2 to h of k in both sets. And because of that overlap, we can then conclude that each of these sets is one color and the same color. Because if h of 2 is in both sets and we've proven that both sets both equal the same color, we can assume that both sets are the same color as horse 2, which then proves that horse 1 through k plus 1 is true. So essentially what that has done now is that has proven that every single horse is the same color. A collection of n horses is the same color. This is obviously ridiculous, but it's not obvious what went wrong. So to figure that out, we have to take a closer look into part of the beginning of the proof. And this is something that I did not catch the first time that I was told this proof. It took me a couple days to figure it out of thinking about it. And so the problem that we have here is we do have the relationship that P of k implies P of k plus 1 in general, but P of 1 does not imply P of 2. That is a faulty relationship that we cannot assume. And the reason for that is because of the method we used to prove P of k to P of k plus 1. That method is not always applicable. That is not something that always works for every single case. As obvious by here, there's a contradiction. And it's quite easy to see once we write out the set of P of 2. There's going to be horse 1 and horse 2. So if we use the same trick that we used here to prove P of k plus 1, we split this up into two sets. Set horse 1, or the set containing horse 1, and the set containing horse 2. Now, the issue with that, obviously, as you can see, is there's no overlap. There's no h of 2 to h of k that both sets share. There's nothing. It's just h of 1 and h of 2. So we can assume that that's the same color, or that that's just one color, and that's just one color, which is, again, common sense, but we can't assume they're the same color. And so the proof falls apart here. It doesn't work. We can't assume it. There's no way to tell for sure that these two horses back in here are the same color. And so thus, the proof is faulty. It doesn't work anymore. And so that's part of the dangers of mathematical induction is, well, I guess not dangers, but you have to be careful about when you're proving stuff, that when you prove P of k plus 1, that it works for every single case and that's not arbitrary and only works sometimes. But that's about it. So like and subscribe, and remember to stream Bjork. Thank you.